So yesterday we left off, we talked about this problem. We left off right here, correct? Remember the 5 steps to using U substitution is to 1, determine your U, 2, solve or take the derivative of U and solve for the dx. That's kind of where we stopped yesterday. So this is our step 2. The reason we want to do that is because if we just do a U replacement or a U substitution within our integral, we have mixed variables. And that's a problem, okay? Because according to my integral right now, U is just a constant value. And is U constant? No, because U is dependent on X, isn't it? So U is also changing. So I can either leave it in terms of X, which we know we can't do, because we can't do the integral at the beginning, or change everything to be in terms of U, including the dx piece. So that's the purpose of solving for dx, to get it in terms of du. Once we have that, we can go back and replace. And remember, this problem is done, so you're just making notes, observations of what I'm doing. Okay? So my third step is to replace the dx in the problem. So I have x squared, I have u squared, and that dx we're going to replace with what we solved out in part 2. And in doing this, I'm hoping, and I'm really, really crossing my fingers that any remaining x's will cancel out as well. And is that going to happen in this situation? Because technically we're dividing by 9x squared, right? So our x squared here is going to cancel out our x squared here, which means now I have an integral that's totally in terms of u, which is great because I can use a power rule on u, can I? Because it's just a variable raised to a numerical exponent. It's a power form, isn't it? Okay. I want to simplify this down before I integrate to get things out of the way, to make it a little bit neat so I don't lose focus on what I have and what I need to do. Okay. So this 9 is not really a 9, it's a 1/9, isn't it? So what I do, coefficients is a coefficient, right? Coefficients don't matter, right? They come along for the ride. They're that mutual friend, which means I can push my coefficient outside of my process. So I'm always going to do that. Push the 1/9 outside of my integral. There's a rule that we learned that allows us to do that. That constant rule. Because that 1/9 is just going to follow us along. And now to take the integral of u squared with respect to u, that's an easy thing to do, isn't it? Because we can use this basic power rule. So, this was my step 3. Right here. Okay? Substitute and simplify. Step 4 is to simply integrate. Well, I can use basic power rule here because it's a number times u to a numerical exponent, right? It's in power form. So u, add 1, divide, and of course a plus c. That was easy, right? Yes? That was my step 4. And then my last step, my step 5, is to go back and put it in the form that it was originally in when we started our process, which was in terms of x, wasn't it? So at this step, I'm going to replace my u with what we decided our u was at the beginning, which is why u is the most important step. And I'm going to simplify anything that I can here. So 1/9, 1/3 gives us 1/27. Okay. And our u, what was our original u? All raised to the 3rd power plus c, and that right there is my final integral. First step, determine my u, right? Second step, take the derivative and solve for dx. Third step, substitute and simplify. Fourth step is to integrate. Fifth step is to replace your u back in. Okay? So that right there, that work right there is all 5 steps. Okay. Take the time right now, make any side notes if you want to make any notes on your paper about the process that I did here. Second one. I'm going to do the second one, and then you guys are going to do the next two. Got it? Okay, so first step, determine my U. Remember, U is always what's inside of our grouping symbol. What do we have grouping symbols up there? We actually have two. What are our grouping symbols up there?
Trig and
Parentheses and trig, right? So it's kind of a double emphasis, right? So what's on the inside of my trig or inside of my parentheses? 5x. So that means my U, right? So there's my step one. Step two is to take the derivative with respect to x. And the derivative of 5x gives us 5. Step two is also to help solve for that dx, right? What am I going to do? If I'm trying to solve for dx, what do? Multiply the dx to both sides, right? Am I always going to be doing that? I did in the first one, right? Will I always be doing that? Well, if you always take the derivative of u with respect to x, your dx is always going to be on the bottom, isn't it? So we're always going to be multiplying the dx. Okay. Get that? And then, where did that 5 come from? The derivative, right? Am I always going to be dividing by that derivative piece? Because I did that here as well, didn't I? Yeah. Okay. Interesting. Patterns. Mathematics. Okay, so I have that. There's my step 2. Okay, so my step 1, determining the u. Step 2, figuring out what the dx is. Step 3 was what? Substitute it in, right? So in our original integral, awesome. Okay, can I simplify this? How? The 5s, they cancel each other out, don't they? Which means I'm left with the integral of just cosine of u with respect to u. Can we integrate the cosine of u? What's the integral cosine of x? Guys, look in your journal. Huh? Okay, we're not sure. So if we're not sure, what should we do? Notes or which way am I going up? Or would I'm going up if I'm integrating, right? That's a terrible question. So I'm here. So what's the integral? Sine. Positive sine of u. It doesn't matter what the variable is as long as we're taking derivative or integral with respect to that variable. Okay? And then of course, plus c. I need to, I don't know if I can.
You didn't.
Okay, thank you. Okay, that's my step 4, and my last step is to plug back in. What's my famous saying when it comes to trig?
With behind the trig stays behind the trig.
What comes behind the trig stays behind the trig. What was originally behind the trig? What's behind the trig now? Even in this process, that is still true. What comes behind the trig stays behind the trig. No. The only time you can change it is do y'all even listen to me right now?
Yes.
It's the week before Christmas and we're all done and we need a break.
Yeah.
Okay. The only time you can change what comes behind the trig is by using a trig identity. Okay. If there's an identity that allows me to do that, I can. But that is the only situation where I can change what comes behind the trig. Got it? Okay. We'll test it on the next one. Okay. Did we get both of them? Thank you, partners, for the great explanations that they did. Thank you. Thank you. Okay. Okay, so the first one, we should have gotten that. Did we get that as an end result?
Yes.
Is that good? Okay, for this one, we should have gotten negative 1/3
Yes.
cosine of 6x plus c. Okay, so let's talk about two things. The 1/3. Do we all recognize where the 1/3 came from?
Yeah.
Okay, so why did it being 2/6, we can reduce and move out. Now that negative, where did the negative come from? The integral of sine. The integral of sine is negative cosine, right? So remember that negative is not really part of cosine, it's part of that coefficient of cosine. And since 1/3 is a coefficient, he's negative, right? Because technically this is what you would have. Correct? But that negative is not part of cosine, it's part of the coefficient of cosine. So coefficients, if there's double coefficients, let's make them 1. Right? Is everybody good with that? Okay. We're about to get a little bit, we're going to start cutting down some more. Okay? We see some patterns. Okay. So, first step, determine your u. Okay, what kind of function do we have here? An e. E for exponential, right? E for easy, right? Okay. Wasn't an exponent one of our grouping symbols? And is there a function in our grouping symbol? What is the function? Negative x squared, right? So that is, in fact, our u. There's my u. Okay. E has an exponent. The exponent is our u. Okay. Now, I'm not going to do all the work that I did earlier. I'm going to go straight to what I want. And what is it that I need? What was the purpose of step 2? Find dx, right? Find dx. Well, I already know the pattern because I've done this 4 times. I'm always going to be multiplying by dx, right? And then dividing by the actual derivative piece. I did that in all 4 examples, didn't I? Or we did that in all 4 examples, correct? Okay, so I know that my dx is always going to be du over the derivative of the u piece. That's always going to be the case. So if I know that's always going to be the case, I'm going to go straight to it. Right? Skip the work. Right? Let's cut down on some of the work. Okay? Step 1, step 2, quick and easy, straight to the point. Step 3 is all about the substitution. So that 5x is still there. I now have e to the u. Like an emu. No laughter. Just silence. Lame. That was lame. It's going to be on video later for somebody to hear. What is that? I've never heard of that. Don't. It's just dumb. Okay. Can I simplify this?
Yes.
What's going to cancel out? Yay, for x's canceling out. We want that to happen in this process. Celebration. And then what is my new coefficient now? 5 over -2, -5 halves, whatever you want to say. Both of those are correct. So I'm going to pull it out of my integral. Because I have a rule that allows me to do that, right?
Mm-hmm.
Okay. So what is the integral of e to the u? E to the u. As simple as that. So this becomes So step 1, step 2, up there, right? Step 3 was the plug-in. Step 4 was the integration, which I just did. And step 5, the final step, is to go back and substitute back in. And there's my answer. Okay. No, it's not that hard. It's not hard at all. It's just about making sure we do things in the right order. Okay. Like this, because there's steps and there's process, and you like when there's steps. Okay, what do we have here? It's a fraction, so it's a rational, right? Does any part of a rational fall within our 8 grouping symbols?
Yes.
What?
The
The denominator. If my denominator is a single term, I can work with that. But when it's multiple terms, it complicates it, right? So take the multiple terms out of the situation. Our denominator here is our u. Okay? So our u here is 16 minus x to the third. Take the entire denominator out. Because then we're going to replace it with a single variable, which is what we want in our denominator. Okay. That means mine dx is the u over negative 3x squared. Let's turn that off. Okay. Do we know where I got that from? Yes, pattern, right? Step 1, step 2, step 3. Is that good? I like that. Our x squares cancel each other out. What's my new coefficient? Negative 1/3, so I'm going to move him out. Oh, I like him. What? That's the natural log. Say it louder.
natural log.
That's the natural log, isn't it? The integral of 1 over u, 1 over x, natural log, right?
Yes.
Hey, that's our natural log function. And then our final step is to go back and plug. Back in. Yeah. Would those absolute value bars be necessary for this particular function?
Yeah.
Okay. The question is, does the inside have the potential to be negative? Yes. I'm subtracting an x, and it's a third power. So that has potential to go from positive to negative, right? So that definitely has a potential to be negative, so we want the absolute value bars.
Should we just like put it in
Yes. It's better to have them and not need them versus not have them and need them. Does that make sense to you? Did you even understand the words that came out of my mouth?
Yeah.
Okay, I just want to make sure you had no change of expression when I asked a question. I couldn't read your face.
I was making sure.
Okay, yes, good. Okay, so we're going to leave it like that. Good? Yes? Okay,
I think it is.
let me go through this one, and we'll see how far we got. Because that one is pretty tough. We haven't done one with a square root. So I threw the odds to the dog right now. So what's my u?
X squared plus 1
Why is x squared plus 1 my u?
because it's under the radical.
Because the radical grouping symbol, right? Yes? That's why it's important to recognize those grouping symbols. Here we have it. So that means dx is du over 2x. We got there? Yes. Okay? Next step says to plug in. Now, it's going to be the square root of u, right? But can we integrate it in that form?
No.
So when I'm replacing, I'm going to also change its form to be in that power form that I need. Okay? So instead of putting the square root of u, I'm just going to simply put u to the 1/2 right now. Let's just do it and get it over with, right? That eliminates one of my steps. Because if I didn't, then I'd have to rewrite I mean, I could do it in the next step. It's the same amount anyway. Okay, so x's cancel out. Why is this a positive 1/2 and not a negative 1/2? Because usually with square roots it's negative and
Because it wasn't at the.
because it's in my numerator already, right? I don't need to move it. Okay, that's usually a big problem. So I really have 1/2 u to the 1/2 du. And now it's in that nice form that I need to use my power rule. The goal is to get into a form where I have an easy rule. So u, when I add 1, because that's what I'm doing during integration, right? When I add 1 to 1/2, 3/2. And I'm going to divide by 3/2, correct? But dividing by a fraction is the same thing as multiplying by the reciprocal. Isn't it? So let's just do it. We know what's going to happen, right? Let's just get it done. That eliminates some work. And then plus c. That's going to help me with my fractions here, isn't it? Okay? So 1/2 times 2/3, those 2's would cancel each other out, right? And I'd be left with 1/3. When I replace, I'm also going to change its form. Because I know that's a necessity, right? So I'm going to have a square root. My u was x squared plus 1. And it is now to the 3rd power. Yes?
Yes.
Were we almost there? Did we get there? Was
Yeah.
it spot on?
Yeah.
Good? With some help? Yeah. It was different.
I just want to make sure.
I recognize that. Okay, the second one shouldn't have been too bad, right? Okay, so let's see. Am I right? Yes? Good. We're getting there. Okay. Last one. Okay, hold on. Hold on. Because I'm coming back to you. You said you can do it in your head.
Oh. Oh.
Oh, okay. So let's think about this one. Okay, I have a lot going on. Don't I?
Mhm.
Technically, I have 2 grouping symbols, right? Because, don't write this down, but technically this is what I have. Correct? Grouping notation, right? So the question becomes, is my u the secant x, or is my u the tangent x plus 3?
Tangent.
Why would you choose the tangent x plus 3?
Because of the parentheses.
Because of the parentheses? Is there any other reason? Well, secant technically has parentheses too, because it's raised to the 2nd power. So it has an inside as well.
I took it as it has like kind of 2 grouping symbols since it's a trig and there's parentheses.
Yeah.
So it brings more emphasis to it. That's how I took it.
How do you take it? I mean, you're right with choosing u to be that one. But technically, I could choose u to be secant x as well.
So you can do it both.
Well, one way is going to work, one way is not. But if I'm determining my u by looking at grouping symbols, technically both of them are in a grouping symbol. Okay? So which one? So this is where I'm going to do some mental. Okay? Because I know I'm going to be dividing by the derivative. Right? As part. Our dx equals du over the derivative. Right? So the question becomes, if I take the derivative of the tangent x plus 3, will that eliminate him? Or if I take the derivative of secant, will that eliminate him? That's the question. Who's going to eliminate who? Anybody remember the derivative of secant x? It's secant x tangent x. Derivative of secant x is secant x tangent x. Okay, what's the derivative of tangent x?
Secant squared.
Secant squared, because it's on my pink sheet and I could always access it there, right? So if I take the derivative of tangent x plus 3, I'm going to get secant squared. Isn't that what the other one is?
Yes.
So who's the
Yeah.
true u? The tangent. Okay? Which trig, you have to play with it to determine which one because they're both grouping symbols. So they both could be the U. Okay, so my U here is my tangent piece. And the reason I chose that is because I know that when I take the derivative of that, I'm going to get the other piece that's in my problem. Because the derivative of tangent x is, in fact, secant squared x. And then that 3 goes to, what's the derivative of 3? 0. It disappears, right? So I don't have to worry about it. So when I plug everything in, that was my U. Get that, right? And lo and behold, which is I knew because I did some forward thinking. Okay? Which when you guys get the use of or the hang of this, you guys will start to see some patterns that you can go straight to the answer. Like I did, hopefully. Let's cross our fingers. Okay. So then U squared over 2. So I'm just gonna put it in front. Is that okay that I did that? Does that bother anybody? Okay, never mind. Because now it's just basic U. That's the simple one. Better? Does that make more sense? Okay. So you had the scrunchy face. Okay. Okay. Not you. Okay, I'm all about the funny jokes today, apparently. Okay.
At least we laughed at that.
At least yes, thank you guys for laughing at you. So I appreciate it. Okay. Are we good? Okay, here is the one exception. And it has to do with the actual function that we can't integrate, that has no official integral value. It takes it, taking it outside of the integral to actually integrate it. It's really weird. Okay. Are you ready for this? So this is a new one. If you have room, I want you to add it. If not, grab a post-it note. We'll do it simple. Okay. If you ever, and this is true no matter what, if you ever come across an integral that has a natural log of x in it, or the natural log of something in it, we cannot integrate the natural log of x on its own. It takes taking it outside of the process to actually integrate with it. So if there's a natural log of x in your process, in your integral, your u is always the natural log of x, no matter what. If there's a natural log in your integral, u is always the natural log of x. If there is a if there's a natural log of x in your integral, your u equals the natural log of x, always. It takes taking him outside of the process to integrate with him in the process. So, my dx is du over, and what's the derivative of the natural log of x? What's the derivative of ln of x? Okay. What do we take the integral of to get natural log? So what's the derivative of natural log? 1 over x, because they're inverse operations, right? U prime over u, x is u in this case. So u prime over u. Well, that's just ugly, isn't it? So how can we fix him? Because he's not right. Multiply by the reciprocal, huh? So really he's this. By multiplying by the reciprocal. Which means when I come up to here, that was my u. Not have that. What's going to happen to the x's? They're going to cancel out. Simplification. And that's what I have. Can I integrate him? He's easy, right? What's his integral? He's a power function, isn't he? A number times a variable, technically raised to a numerical exponent. So u squared over 2 plus c. Yes? Last step. Let's leave them as that. Why not? And there you go. So even though we have a denominator here, because there's a natural log trumps everything for a u, no matter what. Got it?